Okay, good evening, everyone. So here's the continuation of our lesson on metals, and we are now at the chemical reactions of metals. Now, to understand the chemical reactions of metals, we need to understand the reactivity series of metals. This is because metals have different reactivities. Some metals are more reactive, while others are less reactive. So we can order them into this series, where you have potassium right on top. Potassium is the most reactive of these metals. Then sodium, calcium, magnesium, aluminium. And you notice that we have inserted carbon into the reactivity series, followed by zinc, iron, lead, hydrogen. Then you have copper, silver, and gold. So you notice that the copper, silver, gold right at the end, they are below hydrogen. And if it's below hydrogen, you notice these metals are also the same metals that do not react with acids. All right, so this is a pattern that we need to know. Metals that are below hydrogen are unreactive with acids. Okay, and we will come to that very shortly when we do the reaction of metals with acids. But just to recap, the previous time we were speaking about reactions of metals with cold water. So when metals react with cold water, they actually form the hydroxide. So the key word here is hydroxide. So you need to be able to write the equation for the reactions as well as to describe the reactions. So for cold water, only the top four most reactive metals will react with cold water, namely potassium, sodium, calcium, and magnesium. All right, so the metals below magnesium do not react with cold water on their own. Okay, does it mean that they totally don't react with H2O? Now, so the idea behind this is, besides cold water, we could have tried steam. And that's the next chemical reaction that we're going to move on to. All right, so metal plus steam. There is a reaction. All right, however, the reaction differs slightly from that of cold water. Whenever you use steam, what is formed is actually the metal oxide. So you actually form the metal oxide when you react the metal with steam. So it forms the metal oxide and hydrogen gas. So you can see a common pattern. Metals always seem to produce hydrogen as a gas, but the metal compound that is formed actually changes depending on whether you had used water or whether you had used steam. All right. Now, steam naturally is actually H2O in the gaseous state. This means that you have boiled the water to form steam. In order to boil water, the temperature must be at least 100 degrees Celsius. So steam is actually above 100 degrees Celsius. And you can imagine what that means is that the temperature is higher. If the temperature is higher, then the speed of the reaction will be faster. If the temperature is higher, the particles also have more energy to react. That's what we have learned under speed of reaction. Higher temperature, faster speed of movement, therefore more energy to react. Okay? What that means is that now more metals can actually react with steam. Because steam has more energy, more metals are now able to react with steam. So previously with cold water, only the first four metals in the series could react, namely potassium, sodium, calcium, and magnesium. However, now with steam, you have more metals that could react, namely aluminium, zinc, and iron. So even aluminium, zinc, and iron, which are below magnesium, are now able to react with steam, H2O, right? So now let's learn the reactions involving steam. Now for steam, Mr. So will start with magnesium. Why do I start with magnesium? Does it mean that potassium doesn't react with steam? Potassium is very reactive. Potassium reacts with steam. However, potassium and sodium, they are explosive with steam. Because it's explosive with steam, we do not carry it out in the lab because it's dangerous. All right. Calcium is the next metal. So calcium is very violently reacting with steam. So now we have learned the previous lesson. There is a certain hierarchy of adjectives we use to describe the reaction. We start off with very violent. So calcium is very violent reaction with steam. So now if we talk about magnesium, for magnesium, we should say magnesium reacts violently with steam. All right? Because calcium is very violent, therefore magnesium is violent. All right? So if I were to pass a stream of steam over magnesium, the reaction is violent. Now, how violent is violent? Magnesium metal will start to burn with a dazzling white flame. Now, magnesium itself is quite interesting because magnesium is commonly used in fireworks. The very bright color of fireworks is actually produced by magnesium powder, meaning magnesium metal itself. When magnesium metal reacts with oxygen or reacts with other gases, it tends to burn in the gas with a dazzling white flame. It's really, really bright. All right. And the equation is very easy to write. Mg solid plus steam. Now, steam is H2O gas. Please take note. All right. And this forms magnesium oxide as a solid and hydrogen as a gas. All right. This is the reaction of magnesium with steam. Okay. Now, we will skip aluminium, not because aluminium doesn't react with steam. Aluminium does react with steam. However, we will move on to zinc first. Okay, so we have magnesium, aluminium, then zinc. So we shall skip aluminium and go on to zinc next. Okay. Now for zinc, you can imagine, so our hierarchy of adjectives, very violently, then you have violently. Now for zinc, we say that zinc reacts moderately or readily with steam. Okay, so readily is the next level, the next lower level already of intensity. Now, zinc will not burn with any flame. So you can already tell that, hey, zinc is probably not as reactive as magnesium. Magnesium actually burns with a flame that's quite violent, right? So zinc reacts readily with steam. And a solid that is yellow when hot, white when cooled, is formed. So this links back to what you learn in QA practicals. Which solid is yellow when hot, white when cooled, right? Now this makes sense once you look at the equation. We have learned that metal plus steam forms the metal oxide. In the case of zinc, it's zinc oxide. Okay? It's zinc oxide. If it's zinc oxide, naturally it is yellow when hot, white when cooled. That is a very unique property of zinc oxide. Okay? So we have gone from magnesium to zinc. And now we shall move to the next member in the reactivity series below zinc. So just below zinc, we have iron. Iron is below zinc. Therefore, iron is less reactive than zinc. So again, we learn there's a hierarchy of adjectives from very violent to readily. So the next one, iron reacts slowly with steam. All right. Now, how slow is slow? The iron needs to be heated constantly until it is red hot before it can react. So this tells you that, hey, iron must be really, really less reactive than zinc. Zinc can react readily with steam on its own. The zinc doesn't need to be torched, heated before reaction. For iron, you actually need to heat it before the reaction can happen. And the heating is constant. You cannot stop the heating. Besides that, the heating must be quite intense until it's red hot. Red hot means that it's glowing red, the metal. If something is glowing red, right, this means that it's really quite hot. It is like your volcanoes. Volcanoes, when they erupt, the lava that comes out of the volcanoes is red in color. It's glowing red because the lava is really hot. All right, so the iron needs to be really hot before it can react. And this tells you that iron is really, really much less reactive than zinc. Now for iron, the equation is fairly complicated. Okay, so please leave some space in between the chemicals as you write the equation. Okay, so firstly, you see this very, very strange looking formula, Fe3O4, right? You'll be like, oh my God, what on earth is this, right? Why is there this Fe3O4 in the first place? How is that a possible formula? Okay, you might think. Make sense? However, this is actually the correct formula of a compound called iron tetroxide. All right, this is iron tetroxide. So iron doesn't just form iron 2 oxide. It forms iron tetroxide. Actually, if you look at the formula Fe3O4, it's actually made up of FeO and Fe2O3, right? It's actually made up of both FeO and Fe2O3. Okay? Of course, FeO is iron 2 oxide. The 2 is important. Whenever we are asking you what is the cation, what is the iron compound, you need to say, oh, the cation is iron 2, or the compound is iron 2 oxide. The 2 is important because it tells you the oxidation state of the iron. In this case, +2. That means Fe2 plus. Fe2O3 is iron 3 oxide. So again, the 3 refers to the fact that the oxidation state of iron is +3 in Fe2O3. Okay? Now, iron tetroxide is actually made up of iron 2 oxide and iron 3 oxide. Okay? So now how do you balance the equation? To balance an equation like this, always start from the metal. The metal here is iron, Fe. So if you see 3 Fe on the right, you must have 3 Fe on the left. All right, Ken? Next, after the Fe is done, we will do the oxygen. I have 4 oxygen on the right. Therefore, you must have 4 H2O on the left in order to have 4 oxygen. And finally, to balance out the hydrogens, I'm sure you can think of putting a 4 in front of the H2 on the right. So this balances the equation. All right, 3 Fe plus 4 H2O becomes Fe3O4 plus 4 H2. Okay, and this concludes the reactions of metals with steam. All right, Ken? So we are looking at the reactions of magnesium, zinc, and iron with steam. The reason is because for potassium and sodium, the reaction with steam is explosive and therefore is unsafe to carry out. For calcium, the reaction is also very, very violent, so typically it's not carried out. So magnesium, zinc, and iron are the metals which are more commonly reacted with with steam, sorry. Okay, so let me just pause the recording for a short while for you to take things down, as well as to ask any questions if you have, okay? Okay, so we have now completed the reactions of metals with cold water, as well as metals with steam. Please be aware of the differences between the two reactions. And now we move on to the very final one, which is the reactions of acids with metals. You notice that most metals do react with acids. However, not all of them do. So which are the metals which do not react with acids? So if we look closely at the reactivity series, the metals that do not react with acids are the ones that are right at the bottom. Okay, copper, silver, and gold do not react with acids. And that can be predicted by their location in the reactivity series. These metals are below hydrogen. Below hydrogen means they are unreactive with acids. Okay, so we say that relative to hydrogen, they are below hydrogen. Therefore, they are unreactive with acid. Okay, Ken, I think this concept you are quite familiar. So acids, how do they react with metals? So let's quickly finish this. Metal plus acid forms salt and hydrogen, right? In this particular topic, if we use HCl, we will form the metal chloride and hydrogen. All right. So because it's HCl that we are talking about here, the salt is actually a chloride. Okay. So only the metals which are above hydrogen, only the ones above hydrogen are able to react with acids. The ones below hydrogen do not react with acids. Let's look at one such example. Okay, we are only going to look at one example. So I'm sure the simplest example will be zinc plus HCl. Okay, by now I'm sure you know this will form zinc chloride. Zinc chloride's formula is ZnCl2. It is ZnCl2 because zinc in a compound forms zinc 2 plus. So Zn is always Zn2 plus in a compound. Cl has 7 valence electrons. It gains 1 valence electron, so it's Cl minus. So to balance out the positive and negative charge, the formula must be ZnCl2, where you have 2 Cl minus bonded to 1 zinc ion. And it forms hydrogen. To balance the equation, we add a 2 in front of the HCl. All right. Looking at this equation, actually, can't we think of this in terms of a displacement reaction? If you look closely at this equation, can we say that zinc displaces hydrogen from HCl? The answer, of course, is yes. Why not? Right? Zinc is basically displacing hydrogen from HCl. That's why the Cl goes with zinc. The hydrogen comes out on its own as H2 gas. So this is actually a displacement reaction, even though we have never really thought about it, right? Okay, so acid plus metal is in some sense a displacement reaction. And this works because zinc is higher or above hydrogen in the reactivity series. All right, and that makes sense. Because zinc is above hydrogen, that's why it can displace hydrogen. On the other hand, copper is below hydrogen. Below means less reactive. That's why copper is cannot displace hydrogen from HCl. And that's why copper is unreactive with acids. All right. So acid plus metal, one good way to remember which metals react is to look at where hydrogen is. If it's above hydrogen, then yes, it will react. If the metal is below hydrogen, it won't react. Next, for acid plus metal reactions, how can you use this reaction to work out how reactive the metal is? So this is about planning experiments. How to use this reaction to work out reactivity. Obviously, a more reactive metal will have a more violent reaction, right? So what does it mean for the reaction to be violent? It's violent when, okay, things are like rumbling around, the acid is like, whoa, really like effervescence, lots of effervescence, bubbling. Okay, these are signs of a violent reaction. Okay, can so what I've just mentioned, effervescence, bubbling, it's super rumbling around inside the mixture, right? This can be measured. So how then do you measure, all right, the speed of this reaction? So now we go back to the concept of speed of a reaction. So how would you measure the speed of this particular reaction between zinc and HCl? Of course, one very good way of measuring the speed of reaction is to measure the volume of gas given off. How would you measure volume of gas? To measure volume of gas given off, we use a gas syringe. Right? Because the gas syringe must have a retort stand to clamp it. Okay, and this is a typical setup to actually measure the speed of a reaction where a gas is produced. So the gas syringe, of course, is to measure the volume of gas produced. Okay, so a more reactive metal will have a faster reaction. Faster reaction means larger volume of gas produced in the same time. If it produces more gas in the same time, it means it's more reactive. Okay, now we will do this in greater detail, learn how to describe this in greater detail, all right, as we do more practices. But this idea is important. So don't just learn the reaction as acid plus metal. Don't just learn reactivity series on its own. Think, how would you plan an experiment to prove or to work out the order of reactivity? This is actually one very simple and one very good way of working out the order of reactivity of, let's say, 4 different unknown metals. Just put the metal into some HCl, connect it to a gas syringe to measure volume of gas produced. If there's a larger volume of gas produced in the same time, let's say 1 minute, then it's a more reactive metal. Okay? Can? Now, I shall give you some time to copy this down because I think this is quite useful thing to know about. Okay? So let me just pause the recording for a short while. All right. So now that we have worked out the 3 different reactions of metals, so metal plus cold water, metal plus steam, metal plus acid, please ensure you know which metals react with what. This is very crucial. When learning the reactions, also ensure you learn the equations that come with it. It's a brilliant opportunity to practice equation writing and balancing over here. Okay? Now, the order of reactivity of metals is also important for us to predict another category of reactions, which is called displacement reactions. All right, and for that, I suggest we start a new section on its own. Now, displacement reactions, basically the concept behind this is that the more reactive metal displaces the less reactive metal. A good example is magnesium with copper. All right, magnesium is a more reactive metal. Okay, because it's higher, it's above copper in the reactivity series. Now, I've deliberately written this as an ionic equation. How do you know it's an ionic equation? It is an ionic equation because you can see ions with charges. If it had been a full chemical equation, you would not see any plus and minus. The fact that you see a plus and minus here on top as a charge shows you that this is an ionic equation. This is obviously the copper 2 ion. Notice I write the 2. Copper, you have to specify 2, copper 2. Just like iron. Iron, you have to specify as iron 2 ion, iron 3 ion. All right? Now, this is the copper 2 ion. If it's an ion, you must know it is part of a compound. The copper 2 ion, Cu2 plus, written in an ionic equation, shows you that it is already inside a compound. Because it's Cu2 plus, there clearly must be something that is negative to balance out the 2 plus. That means it must be combined with something that is negative, but that negative part is not shown in the ionic equation. Okay, so Mg plus Cu2 plus, the more reactive metal, magnesium. Now you have the Cu2 plus in a compound. But what happens at the end? Of course, you know by now, magnesium being more reactive will displace copper from its compound. Therefore, copper comes out as a solid. You notice when a metal comes out, there is no charge. Why is there no charge? There is no charge because now the metal is on its own. It's an element. It's no longer part of a compound. It's on its own as an element. That's why there's no charge. Okay? If it's a metal on its own, not combined with anything else, there's no charge. Then how about the compound? So what is in the compound now? Now the compound has magnesium inside it. Magnesium inside the compound now should have charge, right? So it's Mg2 plus. Okay? So for the displacement equations, for the ionic equations, whenever there's a charge on that particular substance, this means that particular substance is inside a compound. If there's no charge on it, it's an element. Okay? So how would you describe the observations for such a displacement reaction? So today in class we did solid, solution. Last point, gas. So there are always 3 observations. Actually, there are 4, but these are the 3 that you must talk about. The first one, solid. What solid is formed? If you look at it, on the right-hand side, the solid formed is copper. Copper is a shiny, pinkish brown or reddish brown. Okay, copper as a metal is reddish brown or pinkish brown. Okay, so this is what you have taken down in class today. Next, the solution. Okay, once you have dealt with the solid deposit of copper metal, you deal with the solution. So what is the color change of the solution? So at first, you have Cu2 plus. Aqueous is the solution, right? Aqueous is the solution. Cu2 plus aqueous is blue. So the solution changes from blue to what? In order to determine the final color, look on the right-hand side. The right-hand side, what is aqueous? Mg2 plus. Magnesium. Magnesium compounds are white solids, but as a solution, they are colorless. So the solution changes from blue, which is Cu2 plus, to colorless, which is Mg2 plus. Another way of saying this is the blue color of the solution should fade. That means it becomes less and less blue. And that makes sense because there's less and less Cu2 plus as it's being displaced. Finally, the gas. What should the gas be? As I mentioned today, metals always produce hydrogen gas. Over here, the gas is produced is also hydrogen. But how is hydrogen produced? There's no hydrogen in the equation. There's hydrogen in the water molecule, right? So magnesium reacts with water to form hydrogen. Therefore, hydrogen gas is formed. So a colorless and odorless gas is formed. Then you must talk about the gas test. Hydrogen, the gas extinguishes a lighted splint with a pop sound. All right, Ken? So the gas is hydrogen. Okay, would you also need to write effervescence observed? Yes, you can write effervescence observed. Good. Okay, but the main marks is to do with the gas test. Okay, now the very last point, of course, we mentioned in class, over here, your test tube or your beaker should feel warm. Okay, it feels warm because this reaction is exothermic. Displacement of metals is an exothermic reaction. It releases heat energy to the surroundings. Okay, so these are the 4 main observations that you should write down for a practical involving displacements, let's say. Now, this also applies to your theory exam. Okay, please remember that your theory exam is not just 100% memory work. There is also an element of getting you to think about experiments. When we do experiments, how do you plan an experiment? What would you observe? So this can also come in for your theory papers. Okay, so these are the 4 main points that you should write down whenever you have a displacement reaction and you are asked for observations. Okay, so I shall leave this on the screen for you to take a look, internalize, and digest. All right. Now, and that really brings us to the end of today's revision lesson. We have finished basically the chemical reactions of metals. We have gone through metal plus cold water, metal plus steam, metal plus acid, and also the displacement reactions of metals. Okay, so I hope this series, this lesson has been useful for you to revise some of these reactions. And moving forward, you will be more and more familiar as we go on and talk about other aspects of metals. So the very next lesson, we will use the next lesson to actually revise how do we extract metals from their compounds. Okay, metals typically exist as compounds in rocks. These rocks are called ores, O-R-E, ores, right? So how would you extract the metal elements from their compounds in the ores? So we are going to talk about that next lesson. Okay, yeah, okay, like some games that you play, right? Okay, so hopefully chemistry is more and more a familiar subject to you over time. All right, so let me just stop the recording here. Thank you.